afternoon, friends. I am Dr. Dwivedhi from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad, India. I am in the continuation of aircraft stability and control. Today I am in the lecture number 56, which is definition and terminology of module 1 related to the longitudinal static stability. In today's class, I am going to discuss the following topic to be covered in this lecture. In this, I am going to talk about important terms related for longitudinal static stability, and will be discussed each and every terms which are related for this module 1. These are the topics which are given here. So here, longitudinal static stability, part 1. In this, we have to first topic is what is the equilibrium. Define the equilibrium. So if an airplane is to remain in steady uniform flight, the resultant force as well as the resultant moment about the center of gravity must both be equal to 0. An airplane satisfying this condition is said to be in the state of equilibrium or flying at a trim condition. Suppose, what is the meaning of equilibrium? If the aircraft is flying in such a way that the net forces, the forces which are acting in this, mainly 4 forces, these are the lift which is acting perpendicular upward, the drag which is acting opposite to the motion of the aircraft, the weight which is acting towards the center of the earth, and the thrust which is pulling out of the aircraft. If these all forces are balanced to each other, it means the vertical force lift is balanced by the weight of the aircraft, and the drag which is produced by the aerodynamic action, this drag has to be balanced by the thrust force of the engine. If these are the forces, and also the second condition, there should not be any moment. Any moment means there are 3 types of the moment. One is the pitching moment, rolling moment, and the yawing moment. So all these 3 moments has to be balanced. Means there should not be any moment. Pitching, it should not pitch, very small. It should not roll, and it should not yaw. If all these 3 conditions are met, means all the forces are 0 and all the moments are 0, then we can say that aircraft is in steady state flight and the aircraft is in equilibrium condition. So this is the meaning of the equilibrium of the aircraft. Next, I am going to discuss about downwash and its importance on force and stability. So we can see that once the aircrafts are flying, due to the shape of the body or the fuselage or the shape of the wing, the flow will not remain in the same direction as it is a streamline flow or it is a free stream velocity. It will not be the same. Flow will be changing as per the shape of the body, like the wing, like your fuselage. In every part, your engine, these all parts of the aircraft which are protruded outside will create some turbulence in aircraft, and the wind which is coming in front of the aircraft will not be same as it is a free stream velocity. So whenever flow passes on airfoil, due to its curvature, flow direction after some distance from the leading edge starts coming downwards. This is called the downwash. Just I am going to explain. Downwash reduces the effective velocity and hence lift force. This is also affecting the stability of the aircraft. Okay, so what is the meaning here? Just you can see here, just I will first show in this diagram here. If this is the one aerofoil here, and the wind is coming from here, this is the V infinity. It's supposed to go like this, but it will not go like this. Due to this curvature of this airfoil, it will start like this, and it starts downwards. This is called downwash. Okay, so if it is the second one, it will go from the bottom and it will follow the curvature and it will go like this. So this here, if you see, if you draw a triangle here, this is your free stream velocity. This is the V infinity, which is here at the point 1. But here, if you see, the net velocity is this. So this much it has gone. If it is the epsilon, so this much angle it has turned down. So this is called the downwash, and this downwash reduces the effectiveness of the relative velocity. So this V, now this new V or V prime, so this V prime will not be equal to V infinity. Okay, so this is the downwash, and it is affecting the velocity, the net velocity, and this is also affecting the stability and other aerodynamic parameters of the aircraft. If you can see here, if the flow is coming from this direction, it is a free stream velocity, and once it is touching this will go up like this, it will go. If it is going here, due to this, flow will come and here it will go like this. It will start going like this. So in place of, it's supposed to go like this, but it is starting the curvature, and this curvature makes the aircraft to produce the lift and other aerodynamic parameters. Okay, so these things we have to understand, and this is the importance of the this downwash, and it is affecting lot in our longitudinal stability as well as lateral and directional static stability. So the next point is importance of static margin. So first we should understand what is the static margin, and then we can understand what is the effect of it. So static margin is defined as the distance between the center of gravity CG to the neutral point of the aircraft. This margin gives the state whether the aircraft will be in the state of positive, negative, or unstable. Airplane designers to ensure that CG should not fall behind the neutral point. Okay, so if you see here, if I draw here like this, a horizontal line, and this is your CG, and this is your neutral point NP. So the distance between CG and the NP, this is called the static margin SM. At no cost, if it is CG is start moving towards the NP, here, this is the 1, this is the 2, and this is the 3. So if from the initial position the CG has moved to the point 2 from 1, the distance of this SM1, this SM1 is less than SM2, and if it is reaching to the 3, then SM3 is less than SM2, and vice versa. And as and when SM is 0, means CG and NP are coinciding. So if it is like this, this is the CG and here is also NP. If both are in the same point, it is a neutral stable. It is a neutral stable. And if this is the NP and this is the Your CG is behind. This is the nose. If the CG is behind the neutral point, it is unstable. Okay, and if the CG is ahead, like the previous case, if the CG is ahead to neutral point, it is stable. Okay, so this thing is very important, that CG and this NP both should be in the this point of CG and NP, both are very important, and it's located. If you want to make a stable aircraft, CG should be ahead. So just I will explain in this what is the meaning of CG. This you can see here. If you are, this is the CG point and this is the NP point. So if this CG is going ahead, your static margin will increase and your stability is also increase. But if the CG is moving towards the backward towards the neutral point, then the static margin is reducing and the stability margin is also reducing. As in when this CG is falling on top of the neutral point, both are coinciding, then aircraft will be neutrally stable. Neutrally stable means if it is in this direction, it will remain in this direction. It will not change. And if CG is gone behind the neutral point, aircraft will be unstable. Means if you angle of attack is changed, it will not reverse, it will go above that. If it is going like this, it will, if it is going down, it will fall like this. So it will not recover. So the neutral point and the center of gravity both are very important, and this static margin, the distance between the neutral point and the center of gravity is as much, it is more stable, as less, it is a less stable, as it is negative, it is a negative or unstable. So we have to take care of these all things. Okay, so now I am going for the next topic. It is a elevator control power. It is denoted as a Cm delta E. So this Cm delta E is a dCm by d delta E. Okay, so elevator control power is the stability derivative and defined as Cm delta E. This derivative defines how effective the elevator is in creating the control moment. The larger the value of Cm delta E, the more effective the control is in the control moment. Okay, so this Cm delta E, if I draw the plot, just you can see here. If so elevator control power is the stability derivative and defined Cm delta E. This derivative defines how effective the elevator is in creating a control moment. So if we make like this, just you can see. So this is your horizontal tail and this is the wing. Okay, so here we have to put the elevator. This is the elevators here. These are the elevator. And here is this is the wing. So it is some moment is generated here, Cm. So if we plot, this is the delta E and this is the Cm. So you can see that as you deflect this angle, assume it is a plus or minus. So if it is downward, it is a plus. If it is upward, it is a minus. So as per that, you can see that if it is a minus, it is here. If it is a plus, like this, 0, 1, 2, 3, 4, minus 1, minus 2. And if you see by this, it will, moment also will be different at the different condition. At 0, assume it is here. So, and at 1, it is here. Then 0 at here, this. So, it will go like this. So, this is the Cm delta E. So, if this Cm delta E gives the how much control power your elevator has. So, that is the effectiveness of the elevator and up to what angle you can put this elevator. So, that is the purpose of the elevator control power. I am going for the next. This is horizontal tail volume ratio. Okay, so horizontal tail volume ratio is the ratio of product of tail surface area and tail arm to the product of wing surface area and the chord length. Okay, so just it is a ratio. Just I will horizontal tail ratio. This is the, we can say that it is a ratio of the wing. Just I am drawing the wing here. This is the wing, and this is the chord of the wing. See, this is the chord, and this is the wing. Okay, and if I make here horizontal, and here is the tail. This is the tail. This is the tail. And this is the wing here. So, if the CG is here, so from here to here, this is the distance. This is AC. This is the AC of tail. And so, this is the area, surface area of the tail. So, this is the surface area of the tail. So, surface area I am writing ST. And this distance I am writing LT from CG to the AC of the tail. And this surface area I am writing S. And this is the chord. So this tail volume ratio we can define as tail volume ratio is the ratio of the tail surface, that is ST into LT divided by S into C. So, this is one of the very important parameter to assess how much percentage of the area tail has comparing to the wing. If I say that the volume ratio, tail volume ratio is 20, it means the area of the tail is 20% of the area of the wing. So that is the meaning of the tail volume ratio, and it is one of the very important parameters to understand the aircraft static stability, especially in the longitudinal case. Okay, so we have to next is airplane tail contribution to static longitudinal stability. Very important that how the tail of the aircraft. This is the tail. This is the tail. This is the wing. So how this tail is affecting the aircraft static longitudinal stability. So longitudinal means pitching. So how this tail is affecting. So you know that the forces are generated by the wing. So if this wings are generating, so it will try to make nose up or nose down as per the location of the CG. If the CG is behind the AC of the wing, it will make the aircraft nose up. If the CG is ahead of the AC of the wing, it will make nose down. But how to control? Then these tails are important. This tail will generate the lift forces either upward or the downwards as per the requirement, and it will balance the aircraft. So this is used for aircraft stabilizer, and it is also called the horizontal stabilizer. Okay, so the tail contribution to the static stability of the airplane, that is Cm alpha, if less than 0, can be controlled by proper selection of VH and CL alpha. The contribution of Cm alpha will become more increasing the tail moment arm LT of the tail, and LT or tail surface area ST, and by increasing CL alpha. Okay, so it is very important that we have to understand the contribution of CM alpha. So to have the longitudinal static stability, CM alpha should be less than 0, or CM alpha should be negative. So what is the meaning of CM alpha? The CM alpha, it means if you draw the plot CM versus alpha, and it should fall like this. This is the slope of this curve is here negative slope. Okay, so this indicates that CM alpha is less than 0. So this is the one condition, and second condition is this CM naught. It is called CM naught. It should be greater than 0. So if we are able to meet these two conditions, we can say that aircraft is statically longitudinal stable. And just now we have seen that this VH, horizontal volume tail volume ratio, this is ST into LT by S into C. So this ST-LT is very important. Either we increase ST or we increase the LT, but we maintain this wing is constant. So as we increase this numerator, then the VH volume ratio will increase and the stability also will increase. So this is a very important parameter. Stick fixed neutral point. Okay, so we should understand what is the stick fixed and what is the stick free. Stick fixed means pilot is not doing anything. It is made your stick, the control sticks of your pilots are not touched, but due to the reflection of due to the application of the forces, your elevator and aileron, all the control surfaces may deflect. So but it will remain in the same position. Position will not change due to aerodynamic forces. So stick fixed neutral point is the position of the center of gravity where it yields a condition that the slope of the pitching moment curve is 0. So here CM alpha is equal to 0. So this is called if you draw the alpha versus CM. So if you are getting no slope, straight line, so this is the CM alpha is equal to 0. Means there is no slope. There is no slope. Then it is called neutral stable. Okay, so like this we have to stick fixed neutral point, and like this we have to calculate the neutral point of this condition. Okay, so I am going for the next, longitudinal static stability. So first of all we should understand what is the longitudinal and what is the lateral. So longitudinal axis, the axis which is passing from nose to tail via the center of gravity, this axis is called the longitudinal axis. The axis which is passing from wingtip to wingtip via center of gravity, that is called the lateral axis. And the axis which is perpendicular to this longitudinal and lateral and going towards the earth, that is called the yawing axis. Okay, so longitudinal static stability, the ability of the airplane to regain its original condition after disturbance in vertical plane, X jet plane. So this is the X and this is the jet. So it is pitching. So if it is called the longitudinal static stability, if aircraft is flying like this and due to some gust, I told you it is a stick fix, means pilot is not doing, but if the gust is coming, by the gust your aircraft, it is moved upward. Okay, if the gust has gone and if aircraft is again coming to its equilibrium condition or the initial condition, then we can say that aircraft is statically longitudinal stable. In this, the longitudinal axis of the airplane moves up or down with respect to the lateral axis, and this is happening with respect to lateral axis. Means this lateral axis from here to here, it will remain constant and aircraft will move like this, like this. Okay, so that is called the longitudinal static stability. This is happening and this is called pitching. So in pitching, if it is disturbed, nose will go up and down, and after removal of these external forces which have disturbed, and it is trying, the tendency of this aircraft is to come to its equilibrium or the original initial condition, we can say that aircraft is longitudinal static stable. Now we have to discuss some two important points, and these are the center of pressure CP and the aerodynamic pressure, aerodynamic center. So the center of pressure is the point where the total sum of a pressure field acts on a body. In aerospace, this is the point on the aerofoil or the wing where the resultant vector, that is of lift and drag, acts. So in this point, the total force is supposed to act, and it is the point where the lift and drag, the aerodynamic forces, are acting. The point is aerodynamic center. The resultant of the pressure forces also cause a moment on the airfoil. As the angle of attack increases, the pitching moment at a point, for example, the center of gravity, also changes. However, the pitching moment remains constant at a particular point, which is called the aerodynamic center. So there is a small difference between the center of pressure and the aerodynamic center. In aerodynamic center, we assume a point where there is no change in pitching moment. You change any angle of attack, but pitching moment will remain the same. That is the point. We call it as a aerodynamic center. And for all our stability point of view, aircraft stability and control system, we have to take aerodynamic center, not the center of pressure. Okay, so this gives a very good concept of that it will remain constant for one particular condition. So next is what will happen if the CG is at NP. This I have already, I think, covered. So if I told you just now that if the most of the time CG is ahead of the neutral point, and if this CG is going backward and it is on top of the neutral point, the airplane will remain same flight condition. It means it is a neutral condition, and if it is going nose up, it will start nose up. If it is nose down, it will start nose down. That is called the neutral point. Means if it is disturbed, it will remain in the disturbed condition throughout its flying operation. So it will behave like the airplane is neutral, longitudinal, stable. So this is the importance of CG. When it is falling on the neutral point, aircraft will be neutrally stable, means it will remain in the same disturbed condition throughout its flight. Next is gearing ratio. This gearing ratio is a measure of mechanical advantage provided by the control system, and this G, gearing ratio G, is equal to delta E by LS and delta S. So here delta E is a reflection of the elevator, and LS is the distance, and delta S is the area difference of the distance of the from the hinge point. Next, stick free and stick fixed longitudinal stability. When the control stick from the cockpit is not disturbed, and only controls are disturbed by external forces is called stick fixed. Okay, so pilot is not there, control stick of the inside the cockpit is fixed, it is not moved. When controls are not fixed and pilot apply some force internally to disturb control surfaces, then it is called the stick free. So when we assume that pilot is not there, controls are, nobody is operating, and it is operated by the help of the forces developed by the aerodynamically, then we call it is a stick fixed. But when pilot is sitting and or anyone is sitting in a cockpit and it is operating the control surfaces for up and down, for nose up, for rolling, yawing, pitching, then we say that it is a control stick free. Okay, so this is the difference between stick free and the stick fixed. Hinge moment. Hinge moments are the moment generated due to hinging any movable control surfaces to a fixed surface. Okay, so if you take, this is the rod, and if it is fixed here and there is a hinge here, so it is called the hinge moment. So if you put a force here, it will move. So this force into this distance, it is called the moment. So this is called the hinge moment, and this is useful for the operation of the control by the pilot. So I have taken this reference from the Robert C. Nelson, Aircraft Stability and Control. Also, I have gone through this lecture, NPTEL lecture of Aircraft Stability and Control by Professor A.K. Ghosh, IIT Kanpur. And this is the link which I have given. Thank you very much for joining the class. Please be tuned for my next class, which is related to the aircraft lateral and directional static stability. I am going to cover how the aircraft is, I will discuss the terms related to the aircraft lateral static stability. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.